So we have two more lectures to go. Today, lecture 21 is microstructure analysis techniques. We'll give very brief introduction of scanning electron microscope, X-ray diffraction, XRD, MIP, and some other method. Okay. And the last lecture is Thursday this week. We will discuss structure retrofit techniques, how to repair concrete materials. Okay, and then next week will be your presentation about your term paper. Okay. All right. So here show us one of the previous methods we mentioned before, how to measure the cement compound percentage of different compounds such as C2S and C3S. Okay. So one of the simple methods is called point counting method. Okay. For example, we can take a picture of the cross-section of a compound, and based on the shape, the color, and morphology of different faces, we can count, for example, number of pistons for different faces. For example, C3S, we have light color, angular shape. Okay, and for C2S, we have round, dark colors, and in between we have the liquid phase of C3A and C4AF. Okay, so we have count how many points for different phase, and from there we can calculate and estimate the area and the volume for different phases. Okay, so that's the basic idea of point counting method to get the percentage of different compound in cement clinkers. Okay. We can also use X-ray diffraction method to get a percentage of different compounds. Okay. And here, let's look at how X-ray can be used to do that. Okay. So consider we have a perfect crystal with atoms arranged in order manners. Okay. For certain type of crystal, the distance between atoms will be fixed. Okay. And also, let's look at the composition of waves. Okay. So let's say we have different waves, and the waves has different amplitude. If two waves, 1 and 2, are in phase, okay, like in this case, okay, then the addition result in wave will have higher amplitude. Okay, so when these two waves are in phase, the amplitude will be amplified. Okay. In this case, wave 1 and wave 2 are kind of out of phase. As we can see from here, at distance 0, wave 1 has 0 amplitude, and wave 2 has small amount of amplitude. Okay, and we see these two waves are out of phase. Okay. So in certain situation, it can be completely out of phase. For example, if at certain point, wave 1 has minus A amplitude, lowest point, and wave 2 may have the highest point, A. Then these two waves will offset each other. And in that case, we call that these two waves completely out of phase. And the resultant amplitude will be 0. Okay. So for a certain crystalline materials, as we mentioned, the distance between two atoms will be fixed, such as D. Okay. And let's say we have two waves, wave 1 and wave 2. Okay. So wave 1 is reflected by these atoms back, and wave 2 is reflected by another atoms. Okay. And we can calculate the travel distance of wave 1 and wave 2. Okay. And 2D sine theta is the difference between the distances traveled between wave 1 and wave 2. Okay, and theta is the angle of incident. Okay. And lambda is wavelength, and D is distance between two atoms. Okay, so if 2D sine theta is equal to integer number of lambda, okay, and then the amplitude will be amplified. Okay, because D is fixed for a certain type of crystal, and lambda is also fixed for a given type of X-ray. Okay, so we have correlation between theta and D. Okay, so that's basically how the X-ray diffraction method is based, and we call this equation a Bragg's law. Okay. So for X-ray diffraction method, we change the incident angle, change the theta, okay, and then we measure the intensity of the response. Okay, so that can get a signature intensity versus theta. Right. And here shows example of planes in a cubic system. Okay. For a certain type of crystals, it may have many different type of planes. For example, we may have the green plane, which is A, E, G, and C. The red color is B, E, and G. And also we have blue plane, which is D, F, G, and C. Okay. And for different plane, the nature, the distance between the atoms are different. Okay. And this information is fixed for different type of crystals. Okay. For X-ray diffraction method, we could have two different approaches. The first one is called the Loy method, which we apply the light, which has variable lambda. Okay. The lambda is not a single lambda. We have variable lambda. But the incident angle theta is fixed. Okay. So we apply the X-ray directly on a crystalline lattice. The other method is called the powder method, which is more commonly used compared to the first method. Okay. The sample crystal need to be grounded to powder form. Okay. So why we need to do that, we will discuss in a moment. The lambda is fixed, which means we have only one type of X-ray. Okay. The theta is variable, which means the angle of incident is changing over time. Okay. So the powder method is more commonly used compared to the Loy method. So for the first method, again, lambda is variable. We have different lambdas. Okay, and a solid made by a great number of cells. We do not need to grinding the sample into powder form, and we measure the diffracted rays. Okay. And from that information, we can have an idea of what type of crystals in the samples. For the powder method, the solid sample is reduced to fine powders. Okay. Typically, the size of the grain, the powder particles should be less than 80 micrometer. Okay. For a certain type of samples, the orientation for a given crystalline plane is random. Okay. However, we have so many grains. The number of grains is huge. So some will be properly oriented to diffract along a certain planes. Okay. So as we can see from these pictures, because we have so many number of grains, so for any different type of plane, we have a decent number of grain oriented to diffract along a certain plane. Okay. And each of these cell shows different particles. Okay. And each orientation exists for a great number of occurrences because we have so many particles. The particle size is so small. And the powder is placed in rotating sample holders. Okay, again, we need to ground the powder into small sample into small powders, and they place the sample in the sample holder, and the sample will rotate it around X-ray source. Okay, again, the lambda is fixed, which means we only have one type of X-ray. When rotation angles verify Bragg's law, which means here 2D sin theta is equal to n lambda. Okay, so n is any type of integer. Okay, so when that happens, the intensity will amplitude. Okay, we have a higher intensity for certain theta. Okay. Of course, that is controlled by lambda, the wavelength, and also the d, which is the intrinsic property of certain type of crystals. Okay. Right. So here, example of powder XRD. Okay. This is the Cooper slag. Okay. It's not very clear, but in that sample, we have many different type of crystals. Okay, and for each crystals, it has a signature intensities. Okay, for example, a certain type of crystals, they may have peaks at, for example, 20, 31, and 53 degrees. And the relative height for peaks at these degrees will also be fixed. Okay, it's like a fingerprint for different type of crystals. Okay. And for certain type of sample, we may have more than one type of crystals. Okay, and sometimes these peaks may be overlap to each other, make it harder for us to see what's inside the sample. So for XRD, we could have a qualitative analysis. The goal is to determine the natures of crystalline component. Okay, we just know what type of crystals inside the sample. We do not need to know the percentage for each crystals. Okay, so we can determine the space d for each peak. Okay, and we can also consider the relative intensities, which means intensities as different angles. And we can use that information to match no component. Okay. So the procedure may be very troublesome when we have more than one component, because sometimes we have overlap of the peaks for different components. Software is very useful. Actually, software is necessary to be used to analyze XRD information. Okay, so here shows example. Okay, so this is from a certain type of database. This is for calcite, which is a CA03. For different d, okay, which is the distance between two atoms, okay, which is corresponding to certain theta, okay, for certain lambda. So we have relative intensities, I over I max. Okay, I max is the maximum possible intensity occurs at a certain d values. Okay. So for qualitative analysis, we can check on the phase of materials by comparing two or three types of peaks. Okay. The analysis may be difficult and time-consuming, but with the help of software, it may be very quick to tell what type of crystals in your samples. Okay, it is not very useful for non-crystalline materials, because for non-crystalline materials, the d value is not fixed. Okay, So we cannot use XRD for non-crystalline materials. Okay. The benefit is it is very accurate. We can, for example, we can see crystalline materials such as Asian guy and the calcium hydroxide in the sample very quickly. Okay, but it's pretty hard to see the percentage for these crystalline materials. Here shows the sample problems. Okay, so if we have white fine powders and we want to know what are the crystals in the powders. Okay, so we can have XRD diagram with the theta and intensities. Give us information of lambda. So lambda is the wavelength of the X-ray. Okay, and also we have the SCDD database to compare with. Sometimes we can also do a so-called quantitative analysis of XRD, okay, which means we can somehow calculate the percentage for certain type of compound. Okay, so by adding a known constituent and measure the intensity. Okay, so here is the equation we can use to do the quantitative XRD analysis. So I1 and W1 is the intensity and the weight fraction of one constituent we want to study. And I0 and W0 is the intensity and the weight fraction of a reference constituent, which is the known materials. Okay, so we can change W0, okay, and we can measure the ratio of W1 over W0. Okay, and we can also measure the intensities and also the ratio of intensities. Okay. For example, if we do not know W1 over W0, okay, but we can change W0 and measure that. We can also measure the I1 and I0, which is the intensity ratio for the known and the reference materials. Okay, and we can get many different points. Based on that, we can have an idea of the slope, and based on the slope, we can somehow estimate W1, which is the weight of the unknown materials. Okay, so that's the basic idea to do quantitative analysis using XRD. So that is a very short introduction of XRD. The next method is called thermal gravity matrix analysis. Okay, so this method is very straightforward. We get a sample and we put a sample in the oven and we gradually increase the temperature inside the oven and we record the weight loss of sample versus the temperature. So we can have a curve of temperature versus weight loss. We can use this method to assess, for example, chemically combined water, okay, because that water may lose between certain temperature. We can also check the degree of hydration of cement. Okay. We can also check the quantity of certain type of hydrate, okay, by knowing the temperature when this hydrate decompose, for example, calcium hydroxide. Okay, so here I show an example of thermal gravity matrix analysis, temperature versus time. Okay, for example, if we know the decomposition temperature of calcium hydroxide is around, for example, 500 degrees, and at this temperature, we see a change, the weight change, loss of weight of the samples. And based on this information, we know probably this much of weight is coming from calcium hydroxide. Okay. Again, the idea of this analysis is very straightforward, but we need to know what type of materials before we do this analysis. Okay, so this is the thermal gravimetry method. Sometimes we also call that TGA method. Okay. All right. So the next one is mercury intrusion porosimetry, or we call that MIP method. Okay. We can use mercury to measure the porosity, which is the volume of a pores in your sample. We can also estimate the pore size distribution and even the surface areas inside the samples. Okay. So MIP method can give a fast, accurate pore structure, okay, for different type of materials, not only cementitious materials. So it can give a pore size diameter in the range between 360 micrometer to this is 0.005 micrometer. Okay, so this is 5.58. So the pressure range is from 0 to 33,000 psi. Okay, so around 228 megapascal. So we're using the pressure to force the mercury, which is a liquid metal, into the pores of the samples. Okay, so that's a correlation between the pressure applied and the pore size in the sample. And based on that, we can have an idea of the pore size distribution. Okay, again, we can use MIP for rocks, cement, resins, any type of materials with pores inside, porous materials. Okay. Right. And from MIP, we can have a different type of volume versus diameter because we have a correlation between the diameter of the pores and the pressure applied on the mercury. Okay, so cumulative intrusion volume, differential intrusion volume, and so on versus diameter. Okay, and also the pore areas versus diameter of the pores by assuming the shape of the pores. We'll talk about that in a moment. Before we do that, let's discuss the basics, why we can use mercury intrusion porosimeter to measure the pore volume. Okay. Here shows what is the surface tension. Okay, so a single atom inside the liquid, it is balanced, the force is balanced. But the molecule on the surface, the force, resultant force is downwards. So that's the reason we have a curvature along the surface. Okay, and based on that information, the angle of the curvature, we can calculate and get a correlation between the pressure and the pore size. So R is the size radius of the pores. Theta is the contact angle of the liquid. Okay, for mercury, the angle is fixed for at certain temperature. So around 135 to 141 degree of contact angle for mercury. Okay, gamma is the surface tension for mercury. Is also a fixed value. Okay, so based on the so-called Washburn equation, so that's a famous equation, we have a correlation between pressure we applied and also the size of the pore. Okay, other information, including gamma and theta, is pretty much fixed. Okay. All right. Again, the contact angle for mercury is around 140 degree. Okay, so based on Washburn equation for the pore size of 18 angstrom, that is corresponding to 60,000 psi of pressure. So we have glass container. In the glass container, first of all, we put samples. The sample is oven dried. So we put the oven dried sample in the glass container, and then we vacuum the glass container. So that's the first step. Okay. And then we fill the glass container with mercury, and then we slowly increase pressure so we can force the mercury into the pores of the sample. Okay, so we have pressurization steps, and then we slowly reduce pressure. We call that depressurization step. Okay, so here shows the intrusion and the extrusion curve. Okay. The intrusion and extrusion curve are not overlap perfectly. Okay, the curve in the bottom is intrusion curve. So that's when we slowly increase the pressure. Okay, so increase pressure, we push more mercury into the pores. Okay, so at lower pressure, the mercury is penetrated into larger pores. Okay, when we increase the pressure, the mercury will be pushed into smaller pores. Okay, so then we slowly decrease pressure. Okay, so that is the extrusion curve. Okay, the x-axis is the pressure in psi, and the y-axis is the volume of mercury. Okay, so the volume of mercury basically is the pore volume of the sample. Okay, so the intrusion again occurs by increasing the pressure on the mercury, and extrusion by decreasing the pressure. Okay, at a low pressure, the intrusion is in the interparticle space. When we have, for example, cement particles, we have interparticle space. So at lower pressure, the mercury first intruded for this larger interparticle space. And then when we further increase pressure, the mercury will be pushed into the pores inside the particles. The difference between intrusion and exclusion, we call that hysteresis. Okay, so that's why we have intrusion paths and the extrusion paths. These two paths are different. The intrusion path is lower than the extrusion paths. Okay. So the volume of extrusion will be larger than the volume of intrusion at any given pressure. Okay. So at any given pressure, the volume of intrusion will be lower than volume of extrusion. Okay. So for any given volume, the pressure of intrusion will be larger than pressure of extrusion. Okay, that's shown here for any given volume. Okay, the volume of extrusion will be less than volume of intrusion. All right, at full cycle, after the intrusion and extrusion cycle, okay, we can see when we reduce the pressure to 0, we may have some mercury left here. Okay, so some of the mercury is retained within the pores. The reason for that is because the pores is not perfectly spherical shape. Some of the pores has a bottleneck shape, such as a container. Okay, so the opening of the pores is narrow than the remaining diameter of the pores. So that's the main reason we have the difference between intrusion and extrusion curve. Okay, but eventually the loop will close with small cycles. And each step on the intrusion has corresponding step on the extrusion at lower pressure. Okay. And the first intrusion will fill all of these pores without restricted entryways. So restricted entryways means that we have a bottleneck, smaller entrance for the pores. Okay. And as the pressure drops, all pores with the bottleneck will remain filled up. So when we reduce the pressure, some of the mercury will not go out of the pores because we have a bottleneck, also called restricted entryway. Okay. Anyhow, we can use MIP method to measure the pore size, okay, and also the pore volume, as well as the pore size distribution. We can also get the information of the surface area, in this case, by assuming the shape of the pores as cylinder shape. Okay. So pore size distribution is another information we could get from MIP method. Okay. So this is the pore size distribution. One of the potential drawback for MIP method is when we push the mercury with very high pressure, some researchers said it may damage the pore structure. Measure the pore structure and pore size distribution may not be the true pore structure because, again, the mercury may damage the pore structure when we apply the high pressure. Okay, so that's the one of the potential drawback for this method. And also, mercury is dangerous. Okay, when you deal with this method, always be careful. Next one, SEM. Okay, SEM, the full name is called scanning electron microscopy. This is a very commonly used method to see the zoom-in picture of cement and concrete. So I think we show SEM picture in many of the early lectures. For SEM, we have two different modes. The first one is called backscattered. For backscatter mode, the sample need to be polished, okay, very smooth surface. To polish the sample surface. The second mode is called secondary electron detection. Then the sample is fractured surface. No need to polish the surface. Okay. And for both modes, we can have information about chemical composition based on the so-called EDS. Okay. Basically, we can use EDS to see what type of atoms in certain location inside a sample. So we're going to talk about EDS in a moment. So again, we have secondary and backscatter mode. Okay. For secondary electron SEM, we use one type of electron detector, okay, to collect the so-called low velocity secondary electrons. Okay. The picture will give us a topography, which like a 3D pictures. Okay. So high spot will be bright, the lower spot, the holes will be dark spot. Okay. So we can see like a three-dimensional objects on the fractured surface. Okay. The magnification of secondary mode is very high, so higher than the backscatter mode, the second mode. Okay. So magnification can be up to 100,000 times. Okay, so very, very high resolution. So as we can see from here, we can see a 3D picture with very high resolution. Okay, so this is the sand green. So the second mode, the backscatter mode, use the different type of electron. Okay, this is the high velocity backscattered electrons. Okay. The sample need to be polished, very flat, use different polishing machine. We also need to use epoxy to fill the holes of the polished surface, and then need to polish the epoxy. Okay. So for backscatter mode, it's based on the difference in the backscattered effectiveness. That is, for different type of atom, the so-called backscatter effectiveness are different. Okay, so basically we can see contrast for different element with different atoms. The resolution is not as high as the first mode. Okay, so up to 4,000 times magnification. Normally for concrete and cement, we use backscatter SEM a lot. Okay, this is the picture we see before. Hydrated concrete, these are sand or coarse aggregate particles. Okay. The bright color, we know this is unhydrated cement. Okay. Hydration product is the gray color in between. Okay. And the black color are empty voids. Okay. As we can see, we have a lot of empty voids along the aggregate. And also we can see the cracks here and there. Then let's see how SEM works. Okay. So SEM machine will generate continuous electron beams focused on very small areas of the specimen. Okay. The beam will scan raster patterns, basically like what we type. Okay. From left to right, one line, and then again from left to right, another line beneath the first line, and so on. So we call that a raster pattern. Okay, so we have scanning a raster pattern over a portion of the specimen surface, and then we can get an image later on. Okay, so when the beam is focused on a spot, the microscope will start a raster sweep over a square portion of the specimen. Okay. Okay. One line, another line beneath the first line, from left to right, from left to right, and so on. Okay, so beam travel from left to right, pause, then position itself to create a second line, which is underneath the first line. Okay, and then we do around 512 lines in total. Okay, so here shows the specimen. Okay, pixels on specimen. For every pixels, we have corresponding pixels on the cathode ray tube, which is in the SEM machine. Okay, different pixels, they may have different different color. Okay. Okay. So depending on emission, high emission and low emission, okay, areas with low emission will correspond to darker pistons on the tube, and areas with high emission will correspond to lighter color on the tube. Okay, so the tube we have image of specimen like here. The basics for atom number. So different atom number, they may have different backscatter coefficient. As we can see here, higher number, the backscatter coefficient will be higher, but not so much for secondary electron coefficient. All right. So EDS is called energy dispersive X-ray spectroscopy. Okay, so we can use EDS to see what type of atoms in the spot. So here is the mechanism. So an interaction of electron beams with target atoms will produce a so-called characteristics X-ray of energy. Okay, and X-ray detector within the XEM machine will collect this X-ray, okay, and store them by different energies. Okay. And based on that information, we can see what type of atoms in the certain spot. Okay, as we can see here, for that certain spot, we can see calcium, alumina, silica, okay, sulfur, chloride, potassium, and the Fe. Okay, again, we can only see atoms, but we cannot see what type of molecule in that materials. We could see, or we could guess what type of molecule based on the percentage of atoms, such as calcium and carbonate and oxide. Okay, but we cannot directly see what type of molecule in that spot. Okay. Okay. So here shows how we can see different type of phases in hydrated cement paste. And we know this already. The brightest phase is always unhydrated cement. Okay, and the second brightest phase will be calcium hydroxide. Okay, we mentioned about this several times before. The brightest color is unhydrated cement. The second brightest figures is the calcium hydroxide, and the darkest color is the empty space. Okay, and we can change the grid level so we can see the difference between cement minerals. Okay, again, this is the typical pictures. The brightest color, unhydrated cement. We can see some of the calcium hydroxide here and there. And the grid scales in between the sand particles will be hydration products. And black color is empty voids, like in this crack, and also in the boundary between aggregate and hydrated cement paste. Okay. So with some experience, we can very easily to tell what phases are in the sample. All right, and this is the lecture we discussed microstructure analysis. Okay, so we talk about XRD and also SEM. So these two methods are by far the most commonly used microstructure analysis to tell what phases may in the samples. Okay, there's limitation for this method. For example, XRD can only see crystalline materials such as ethylene and calcium hydroxide. It is not very easy to see glassy phases such as hydrated hydration products such as CSH. Okay. For SEM, we have two modes. With some experience, we can easily tell what phases are in the samples. Okay. We can also see what atoms are in certain spots using the EDS from SEM. Also, we discuss mercury intrusion pore symmetry. We can use that method to study the pore size distribution, pore volume, and surface area. Okay, and thermal gravimetry method, the TGA method. Sometimes we can also use that to tell what the phases are in the samples and even what percentage sometimes for these phases. Okay, and that's it for today's lecture. And we have one more lecture remaining, which is the structure retrofit method, which will be discussed Thursday this week. Okay.